This detailed example deals with hypothesis testing, and it uses the random sample of 20 cases from the 2012 General Social Survey. So suppose that we wanted to conduct a hypothesis test about the variable education. Let's just hide the remaining variables so that we don't have to worry about them. So suppose that we wanted to test the hypothesis that the true population level of education on average in the population was 12 years. So what we can do in this example is look to see whether the value from this sample is different from 12. And so what we have to do is we have to start by getting the sample mean and the sample standard deviation. So I can write the sample mean as basically y bar. So remember, if I take my push or acute sign and I make it symbol font, that creates an overbar. And then I can write s sub y here. I can make this y a subscript. And I have my notation. And so how do I get the sample mean using Excel? Well, I can just use Excel's built-in average function to get the sample mean. I would just make some cell equal to the average of some array of numbers. And then I could get the standard deviation using Excel's stdev function. So I find here that the sample mean is about 14.1 years, and the sample standard deviation is 2.69 years. So I see that my sample mean is bigger than 12, and the question is that due to some kind of real difference in the population from which the General Social Survey was drawn? That is that population somehow different from the entire population of people? Or is this high value just a matter of sample fluctuations? That is this an unusually educated sample of General Social Survey respondents? Well, in order to figure that out, we have to use hypothesis testing. And so we need to look at the steps of hypothesis testing. And I've outlined those here. So the first thing that we have to do is we have to list our assumptions. And our assumptions have to do with three things. One is the level of measurement of the variable. Two is the method of sampling. And three is the shape of the sampling distribution. So the first assumption is that education is measured on an interval ratio level. And then the second assumption is that we have a random sample from the General Social Survey. The third is that our sampling distribution is normally distributed. Now, this might be somewhat problematic in this case because we've got a small sample of cases. Remember, the central limit theorem tells us that as long as we have a sufficiently large sample size, about 30 cases or more, the sampling distribution is going to be normally distributed. However, we only have 20 cases in this case. And so in order to guarantee that this assumption is true, we're actually going to have to assume that the variable education is normally distributed in the population. Okay, so now that we've stated our assumptions, let's move on to our hypotheses. And we have two hypotheses. The first is the null hypothesis. So this is the thing that's actually being tested. And so we're going to assume under the null hypothesis, h sub 0, that mu sub y, which here represents the true population mean from which the GSS was drawn, is equal to 12. And our research hypothesis, h sub 1, is that mu sub y, again, this is the population mean from which the GSS sample was drawn, is not equal to 12. And here we also have to state our alpha level. So I'm just going to state that our alpha level, and I make this a symbol font, is equal to 0.05. And so remember, alpha is the chance of committing a type 1 error, that is, getting a false positive. Okay, so the next step in hypothesis testing is to choose a sampling distribution. And we basically have the choice of two sampling distributions. We can either choose the z distribution, or we can choose the t distribution. And so we have to figure out which of these is more appropriate in this case. And so on what basis do we choose one or the other? Well, it has to do with whether or not we're given information on the true population standard deviation. And so going back to our original data set, we see here that we don't have the true population standard deviation. We only have the sample standard deviation. And so we have to estimate the true population standard deviation with the sample standard deviation. And that introduces more sampling error into our estimation. And so the appropriate choice in this case is the t distribution, not the z distribution, because the t distribution correctly takes into account the additional sampling error. And so we would have to choose the t-distribution rather than the z-distribution. So we have to choose the appropriate formula for the t-distribution. And so what is that formula? Well, it turns out that the formula for the t-distribution is the following. The formula tells us that the t-value, our t-obtained value, is equal to the sample mean minus the value of the true population mean, or the one at least assumed under the null hypothesis, divided by the estimated standard error of the mean, which is equal to the sample standard deviation divided by the square root of n. And our test statistic, our t-value, follows a t-distribution with n minus 1 degrees of freedom. Okay, so the next step basically is to calculate our test statistic using the formula. So let's take a look at how to calculate that. And so we can basically use this formula. And so the formula tells us to take our sample mean, which you'll recall is equal to 14.1. We subtract the value of the true population mean under the null hypothesis, so that's going to be 12. And then we divide that value by 2.69, which is our sample standard deviation. And we divide that value by the square root of 20, which is our sample size. And so we can do the calculations in Excel. And so in our numerator, we're going to have our sample mean subtracting our population mean, our mu sub y, and we'll make that symbol font. And so that's going to equal 14.1 minus 12, or 2.1. In the denominator, we're going to have our standard error, which again is equal to our sample standard deviation divided by the square root of 20. That comes out to a value of about 0.60. And from that, we can calculate our t-value, or our t-obtained, which is going to be the ratio of the difference between the sample mean and the population mean divided by the standard error. And so we're going to get a t-obtained value of 3.47. And so how do we actually conduct our hypothesis? How do we actually evaluate our hypothesis? Well, we need to compare our t-obtained value to some kind of critical value. So let's just call this t-obtained. And now we have to find the t-critical value. So which is the appropriate critical value for this case? Well, if we go to our t-table, we have to figure out first whether we're doing a one-tailed test or a two-tailed test. And so what does this depend on? Well, let's go back and look at our hypotheses. So remember that our research hypothesis is that our unknown population parameter, the true population mean education from which the general social survey sample was drawn, is not equal to 12. And so that means that this is a non-directional hypothesis. It can be either evaluated in the left tail of the sampling distribution or the right tail of the sampling distribution. That means that this is a two-tailed test. And so going back to our table, we're going to be looking at the alpha values here. Since this isn't a one-tailed test, we're not going to be looking at the alpha values here. Okay, so which of these alpha levels should we choose? Well, again, going back to our hypotheses, remember that we said that we're going to choose an alpha level of 0.05. And so we're going to be looking at a two-tailed test, 0.05 alpha level. But which of these values should we choose? Well, we have to figure out our degrees of freedom. And so recall that degrees of freedom are calculated as the number of cases, n, minus 1. So we've lost 1 degree of freedom because we had to estimate the true population standard deviation with the sample standard deviation right here. And so we're going to look at a two-tailed test, 0.05 alpha level, with 19 degrees of freedom. And so that means that our t-critical value is going to be 2.093. I can just round that to say 2.1. And so we have to do the final step in hypothesis testing. We have to compare our critical value, which again is 3.48, to our our obtained value, t obtained value, to our t critical value, which is about 2.093. And so we notice that our t obtained is bigger than our t critical value. And so we can reject the null hypothesis. The other thing we could do is we could think about this in terms of a rejection region. And so if we go back to our Excel file, and if we bring up that program that makes normal curves, we can think about this in the following way. Here's what a rejection region looks like. Now, if you round our critical value to about 2.1, that means that our rejection region is basically for values that are beyond negative 2.1 or values that are beyond positive 2.1. And so if we find a critical value, if we find a t obtained that's either out here or out here, we can reject the null hypothesis. And so remember that our t obtained is about 3.48, which is somewhere out here. And so that's within the rejection region. And that's another way that we could reject this null hypothesis. And so our conclusion basically is that the null hypothesis is unlikely to be true. In other words, the population average education from which the general social survey sample was drawn is probably not equal to 12. And so we have evidence for our research hypothesis that it's different from 12. And so that's what we conclude. We conclude that the true population mean is not equal to 12.